Excellent. Okay, so this is the book. I as well as shamelessly plugging the book, I'm pointing out that this book is about the fine tuning of the universe for life, and my co-author is Geraint Lewis. Geraint's a colleague of mine. We were at Sydney University together. He was my honours supervisor at one point. I'm now at, sorry to correct your introduction, I'm at the I'm at Western Sydney University, not Western Australia. That's about 5,000 kilometres away, so it's only a small hop and a jump over there. We wrote the book together, but I'm a theist and Geraint's an atheist. But there's 7 chapters of the book that we wrote together, so that's what an atheist and a theist can agree on. Now, we're not necessarily right, but hopefully that takes out at least some of the sort of bias or the suspicion that this is just, you know, religious propaganda. So I'll be able to draw a line in my talk between the stuff we agree on and the stuff that we don't. We've often done sort of, actually we did one a couple of months ago, we did sort of a double act where we present the science together and then present what we think it all means separately. So the fine tuning of the universe for life, let me start there before we get into the argument itself. So we're astrophysicists, which means we have great pictures of the universe to look at. This is the center of a galaxy, as well as being wonderful to look at, and that's a real bonus if you're doing this for a living. What we see here is different forces of nature playing out against each other. You can see that things are sort of denser in the center there. That's the center of the galaxy, so gravity is pulling things in, but there's also pressure forces, there's gravitational collapse, there's star forming, there's light bouncing around. There's all sorts of these all sorts of processes coming together. As we dig down underneath, we find that we think we can explain an awful lot about how the universe works by a combination of fundamental forces playing out in our universe. So just to give you a couple more pretty pictures, here's a supernova explosion. I don't know how clearly that's coming through on your screen, but you do owe it to yourself to get onto the Hubble Space Telescope website and the James Webb's website, and get yourself a nice high-resolution screen and a dark room and some Beethoven and a nice scotch, and really make a night of it. So I could do this with pretty pictures all day. Here's the point. What we want to know as a physicist, when you look at these sorts of things, what you want to do is put it into the form, your understanding, the sort of form of explanation that we want as a physicist. We want to know, what were the initial conditions? What can I assume is a starting point for this particular system? And then what laws play out to shape the system in this particular way? So the way that physics explains has this familiar shape. There's general laws and there's initial conditions, but there's a sort of third thing there, which doesn't often get mentioned, but it's extremely important for what we're doing today. There are these constants in the laws of nature. So when we write down mathematically, say, the law of electromagnetism, how charged things interact with each other, we find that in the equation itself, there's a number that we need to put in. The reason that's important is usually what we want from an equation is numbers to come out of them, so to speak. Those are the sort of predictions. And if they match what we see, then we think we've explained something or at least successfully predicted it. But these constants have to go in. So, for example, how heavy is an electron? You hopefully know of electrons. They go around atoms. That's as much as we'll probably need to know today. They have a certain mass. It's a very small number. That's one of the, or at least related to, the fundamental constants of nature. We don't know why that number is what it is, but we can measure it very carefully, and we can consider the question of what if it had been different. That's getting slightly ahead of myself. The reason why this topic turns to the constants of nature, and really to the initial conditions as well, is as following. In any sort of model that you propose as a physicist, where you've got free parameters there, they're sort of adjustable dials, and you want to have some sort of handle on what happens if I change these dials. What would happen if I put slightly different assumptions in, just to see how sort of robust your model is. So what role do these constants play in the universe we see around us? Because, I mean, we're doing fundamental physics. This is precisely what we're trying to explain. So here's a very simple sort of, well, actually, it's going to look rather complicated, but here's a breakdown of what's going on here. If fundamentally you're made of 3 particles, there's more out there, but you're made of 3, essentially. They are called, and there's no exam later, so it's all fine, the up quark, the down quark, and the electron. There might be more basic things than those. We don't know about those now. That's the starting point for the standard model of particle physics, as it's called. Now, what does the universe do with the 3 pieces that it has available? Well, the first thing it does is it can combine up and down quarks into protons and neutrons. That's very nice. Can we make anything else? Well, thankfully, protons and neutrons can stick to each other, and so they will make nuclei of atoms. So, yes, protons and neutrons stick. The electrons go around the outside. That's all great. There's not just one way of doing this. This is the carbon atom, just in case you're interested. There's the entire periodic table worth of ways of doing this. Which element you are in the periodic table depends on how many protons there are in the nucleus, for those who are forgotten their high school chemistry. If you have different chemical elements and you put them close to each other, the electrons, rather than just going around their own home nucleus, I should say, can take a complicated path around the outside of the whole sort of Mickey Mouse shape you see here, holding the whole thing together. And that's how you get a water molecule as a separate entity in itself, as something that holds itself together. This is the fundamentals of chemical bonding. If you put enough nuclei in the right order, of the right kind, you can literally write code for proteins. This is DNA. Hopefully you're familiar at least with that name. And what those proteins you can do with those, and here I'm getting way outside of my expertise, is you can make cells, and I'm told if you put enough cells together, you can make small people who you have to drive around on a Friday night. So why does the way back the electron matter? Why does it matter? Well, because the electrons are here at every stage. Everything builds up from the bottom, or at least a lot of things build up from the bottom. So if you started messing around with electrons, it could filter all the way up. This is what we didn't know until we really got down, once the sort of basics of the model were worked out, and asked ourselves, what if the constants of nature had been different? Again, anytime any scientist has a model with 3 parameters in it, people, you will ask yourself, what if the constants of my model, what if the 3 parameters of my model, what if they were different? What if, is everything very fine-tuned, or is it robust? These are the sorts of questions you ask. Here, we're just doing it with the fundamental constants of nature, as in the numbers that appear in the deepest theories we currently know about and have tested well. Okay, so let me take you on a quick tour through what happens if you change these numbers. If we have, given that we have 3 numbers in that previous screen, the up quark, down quark, and electron, they all have a certain mass. It's not 0. It's a number we can calculate and measure. Sorry, it's a number we can measure, to be more precise. So those 3 numbers, what if they be different? What we can do is represent the possibilities with a 3-dimensional space. Good. So there's the up quark, down. Okay. Sorry. If I occasionally stop, it's because the echo comes back through very, very slightly, and I think someone's talking. So that's I'll just keep going until someone really starts shouting at me. All right, we're good. Treat this block as a menu. That's the way that you can do things. Treat this block as you pick a point in this block, and that's chosen 3 numbers for you. And with that choice, we can then take those numbers, put those in equations, and see what would happen. Now, a little bit of technical detail. We've cut the block off at the top because there's a limit to what our equations can actually predict. We just don't know what's going on to the larger side, so up and sort of to the positive extremes of those axes. There's a technical reason why it's cut off 60 orders of magnitude below that scale. I can give you the name of that if you really want to get into those sorts of details, but there's a nice wide range there that we're exploring. And again, for those who know about these things, these are logarithmic scales. Just gives us a chance to see what's actually going on here. What that means is rather than, this is a standard thing to do, especially in astronomy, rather than going 1, 2, 3, 4, 5, 6, 7 up the side, you go in powers of 10. So every step up is sort of 1, 10, 100, 1,000, all the way through. So treat this as a menu. You've got to order off the menu. Here's, you can see there, you are here. That's the universe that we are in. That's the order we got. What if we change those? What if we moved around to somewhere else in the block? What if you ordered from somewhere else on the menu? Well, let me help you out here. Let me carve off bits of the block that you probably don't want to order from, and I'll explain why. So, for example, I've carved off 2 sections around the back that you can see there. The reason why you want to avoid those sections is as follows. Remember, in our universe, we have up quark and down quark. They can make protons and neutrons. In these universes, that doesn't happen. Instead, and this is getting into details that you don't really need to get into, but over here, you can make the delta plus, and over here, you can make the delta minus. Super exciting, I know. Here's why that matters. The delta plus plus, once you've made it, it will not, it's the only thing, right? There's no other particle. Remember, protons and neutrons, we've got 2 kinds. This only has 1 because it's by far the most stable thing. It will not stick to itself. That's a crucial point. So that's a problem, because what that means is the atomic nuclei you can make consistent of one of these, and that's it. You can't build up the periodic table by putting more of these things together. It's a bit like a Lego set where the basic pieces, you can join 3 of them together, but that's the biggest thing you can make with your Lego set. Similarly, over this side, the delta minus will not stick to itself. So if you shave a little bit more off, there's areas where you can actually have the following take place. Here's a picture of a very, very classical picture of an atom. No quantum mechanics inside here, thankfully. With a proton and a neutron stuck together. This is deuterium. What happens if you sort of go a little bit closer to that boundary that I just showed previously is the neutron will no longer stick to the proton. No neutron will stick to a proton. Right? Actually, there's all sorts of funny things you can do around here. You can even have universes where the electron doesn't go around. It spirals into the nucleus. Anyway, allow me to explain what happens next. Here's the periodic table again. This is the astronomer's periodic table, by the way. It's colored according to where that element is made in the universe. So whether yellow ones are made in small stars, or green ones in large stars, supernovae are needed for the sort of some of the bigger ones, and some that human beings made. If, just to fully lay out the consequences of what we've done by ordering from the wrong bit of the menu, if protons and neutrons won't stick to each other, then this is now your periodic table. Right? You get hydrogen, the end. That's it. That's all you can make. Right? You can't stick 2 protons together, even if you have neutrons. It just, nothing happens. This arguments behind this are actually quite simple, because they're about whether a particular state is stable or unstable. So they're quite simple energy arguments. You don't actually have to do a lot of detailed modeling for a lot of these systems. In this universe, if all you've got is hydrogen, the only thing you can make out of that is a hydrogen molecule, and that is the end of chemistry. That's all you can do. This slide is the only slide you need to show in your chemistry lecture. The lecture probably goes for about 10 minutes, and half of that's probably explaining why the assignment's going to be really easy. It's just a really boring universe. Again, mathematically, everything's wonderful. It's all consistent. It's all fine. It's the laws of our universe, just with some minor tweaks to these numbers. Mathematically, everything's great. It's just that nothing sticks to anything. When you do the work of saying, okay, will this particular system be stable, or does it have enough energy to pull itself apart? You just almost always get the answer, no, it'll pull itself apart. With these sorts of constraints, we can, and we do this in the book in chapter 7, chop off more and more bits of the cube, of the block, until this is the only bit left. Outside of here, electrons spiral into atoms, and nuclei aren't stable, and or everything turns into neutrons, or stars can't shine because nuclei are the fuel for stars. So there's no way of making a stable energy source purely that's gravitationally bound and nuclear powered. And this is what you have left over. This is a picture of the fine-tuning of the universe for life. If you want to put a picture in your mind, this is a good one to sort of stick in there. A wide range of possibilities, and all of them mathematically fine as far as we can tell. There's nothing about the equations where their consistency could depend on this number versus that number. That'll be like saying that, you know, a cube could be 1 centimeter across but not 2 centimeters across. There's just no reason to think that there's any sort of constraint like that. But when we ask a question like, you know, could anything interesting happen? And in this case, it's not even could life happen. It's how many stable elements would you get in the periodic table? Like what sort of complexity could you make out of the fundamental pieces of the universe? On almost all of the space here, you get the answer, you know, almost no periodic table, all really boring. And in this one thin slice, suddenly you get 92 natural elements, you get chemical bonding, you get water, DNA, and proteins, and cells, and people, and wonderful things can happen. It's now very relevant that these are logarithmic scales. If I did this plot using linear scales, just going from the limits, you know, below and above, the screen you're looking at would need to be a couple of light years tall. So, yeah, that gives you some idea of how small this particular space is. Let me run through a couple more examples of fine-tuning just to get a sort of taste for it, and then we'll move on to what this all means. Here's a real video of the sun taken by NASA with a very specialized instrument, of course. Don't stare at the sun. What's happening in a sun? Stars are actually remarkably straightforward to model. That sounds odd, but they're remarkably simple systems physically. The short story is that gravity is trying to push or pull everything to the center, and heat or pressure forces, air pressure, gas pressure, is stopping the star from being completely squished. And if you go and look at where can these, you know, under what conditions can these forces be balanced against each other, the answer is in the regime where you have a star. And if it's big enough, it'll get hot enough in the center, because you need heat, for nuclear reactions to happen, which will then keep the star hot for a very, very long period of time. The question now is, what happens if I start messing with these forces, particularly thinking about the strength of gravity here? Well, it turns out that if you make gravity stronger, you tend to make stars smaller, and that would be all right. So, you know, you just have a scale model of a star, except that you start to get into a regime where things are so hot at the center that the star overreacts if it compresses a bit or expands a bit. So rather than having a stable star like the sun, you have one that pulses and then can blow itself apart. Basically, anything big enough to burn is big enough to blow itself apart if you make the strength of gravity too strong. But we're in a lovely place where our stars are nice and long-lived and stable, and they can power things like us. Final example. This is closer to the work I actually do. This is a simulation done via a group at Durham University and Leiden and a few other places. This is called the Eagle Simulation Project. You get a supercomputer to model a great big chunk of the universe, a chunk where the sort of dots you're seeing here are roughly galaxy-sized, and you have the expansion of the universe and gravity bringing things together and star forming. You put all that physics into a supercomputer and let it whir away for a month and a half. And what you get at the end is what we think is the process that makes galaxies. The short story here is, while the universe starts almost smooth, as you can see, the dense bits of the universe get denser because they are able via gravity to draw other parts of the universe in. So you end up with a universe where you see empty bits, which are cosmic void, say in the bottom right, you can see one there. You get the very dense bits, which are lit up in sort of bright yellow and white, where the galaxies form. And in between, you get this sort of web structure. This is called the cosmic web, where there's bits of the universe that don't quite know which way they want to go. What we did, my colleagues and I, is, I haven't pressed play. This is a video, but it's not playing yet. Let me explain. We took the same simulation code, the Eagle simulation code, and we changed a number, that's given the label capital lambda. It's the cosmological constant. Now, it keeps getting longer. 25 and a bit years ago, 1998, we discovered that the expansion of the universe is accelerating. This is a major result that won the Nobel Prize in 2011, I think, for those who discovered it. That's an unusual thing. The expansion of the universe is accelerating. Some galaxy out there is not just getting further away from us. It's moving faster today than it was yesterday. Very strange. Because the ordinary stuff of the universe is trying to draw things in. It has attractive gravity. But there must be something somehow pushing. Well, we're not entirely sure what that is, but we do have a number that gives it strength, and that's this cosmological constant. One of the problems, invitingly called the cosmological constant problem, very mysterious, is precisely the fact that, we have a candidate for something that could do this from our understanding of particle physics. But when we tried to work out whether the size of that factor and the size of the observed cosmological constant were sort of close to each other, we found actually they are about 120 orders of magnitude apart. So 10 to the power of 120 different. That's a worry. And the reason it's a worry is because if the cosmological constant had been even slightly larger on that scale, remember, you've got 120 orders of magnitude to work with, let's add another magnitude or two, right? That's what this simulation does. We had sort of back of the envelope calculations, but we wanted to throw the sort of the best way of calculating the structure in the universe at these sorts of things. So when I'm about to press play, you've been staring at this boring screen for too long. On the left panel, it's in thirds. The left one is roughly our universe. The middle one is, let's throw in 10 times more cosmological constant. And the right one is, let's throw in 100 times more. Remember, on a scale where the universe is more than capable of throwing in 10 to the 120 orders of magnitude more cosmological constant. So we're playing, we're off. They all roughly start out the same, as you can see. They look fairly similar. But because this number makes the expansion of the universe accelerate, what that means is everything over on the right starts getting further away from everything else. So every galaxy that forms, or a bit of a galaxy that forms, finds that the gas that it would like to sort of eat and swallow to grow is all dragged away by the accelerated expansion of the universe, and there's a very narrow window in which galaxies form. In the middle, you can see there's one galaxy that formed before sort of everything else disappeared in this little bit of the universe. Anyway, over on the right, there's our universe, or one very close to it, doing all the wonderful, lovely, beautiful things of making galaxies in which you make stars and then planets and life and all the wonderful things we know about happen on the left. And all of that gets shut down on the right for a very basic reason. Everything's too far away from everything else. So as I said, on the scale of what that number could have been, you have an awfully small looking region here where anything interesting happens at all. Obviously, add a few more zeros and pretty much, I mean, no galaxy that forms, no bit of the universe, becomes overdense. Keep going, and like no proton ever touches another proton in the history of the universe. So here is the summary of all the possible values of the fundamental constants of nature, the subset that permit the existence of life, or really any sort of complexity required by life, seems very small. This is the sort of point where I can draw a line in the sand and say, if my colleague Geraint was here giving this talk, he would give it, up until now, have given a very, very similar talk. Some of the slides I've used actually were made by, the star slide was actually made by him. I just borrowed it. An atheist and a Christian can agree on the science. That doesn't mean we're right, but it, hopefully that sort of in some way controls for any kind of religious bias. So now we can say, what's the fine-tuning argument? Does this actually prove anything? And that's an interesting point. One of the things that led Geraint and I to write this book, we were colleagues at the University of Sydney, worked on a bunch of things. As I said, I'd been his student and was his postdoc at the time. And I had read the scientific literature behind all the things I've been talking about so far. What happens if you change these numbers? The fine-tuning of the universe for life. I gave a talk to the astronomy group at the University of Sydney. I'm at the University of Western Sydney University. But at the time I was at Sydney University. And there's a group of astronomers there, professors down to master's students, a whole bunch of people. And I gave a talk. And I don't know what things are like in whatever departments you guys are in, but the way it works in astronomy is you give sort of a 50-minute talk. You leave 5 minutes for questions. Questions usually take 2 minutes because, you've explained things well, hopefully, and then everyone goes to lunch. And what happened in this talk was I thought, I bet there's going to be a lot of questions because this stuff I think it's interesting at least. I bet someone at least will find it interesting, so we'll at least get questions from them. Anyway, I talked for about 40 minutes, and then everyone sat around in the room for an hour and a half, all talking about this fine-tuning of the universe for life, trying to work out what on earth this thing meant. And what was interesting to me was there were a lot of opinions about what it meant. They were all strong, and many of them were quite different. So this is the sort of topic where people are pretty convinced either that it definitely means something, or that it's dangerously close to meaning something that it doesn't mean and so must be shut down. It's that sort of, it's a dangerous, either a very useful factor or a very dangerous one in some sort of sense. But let me try and do something with it just to sort of bring us up to speed. My favorite summary of fine-tuning is the following. I'm not religious, but something weird is going on here. That pretty much sums it up pretty nicely. Here's how I present the fine-tuning argument. Hopefully you can see this in anything like the detail in which I'm seeing it. It's a slow motion video of a hummingbird. There's something about nature around us, which even though it's sort of, red in tooth and claw, and there's all sorts of imperfections, and sure, the panda's thumb doesn't look entirely perfect. Nevertheless, there are some just astounding things out there in the world which are just there for us to discover. We didn't make them, they're just there. And it's sort of quite understandable that when people see this sort of thing, they think that someone has put the universe together. Someone with astounding abilities and foresight and knowledge has put the universe together, or at least bits of the universe in some way or another. You don't have to stare at the universe for too long at a hummingbird to think, that sort of thing doesn't just happen, surely. Now, I'd been using this illustration for a while, and suddenly, one day, Facebook tried to sell me this. So if you can see that this thing needs a designer, surely you can see that the previous thing, the real hummingbird, needs a designer, or at least some sort of pretty remarkable explanation. Now, what's interesting is that on the biological level, Richard Dawkins admits this point at least. Biology, he says in The Blind Watchmaker, is the study of complicated things that give the appearance of having been designed for a purpose. Physics is the study of simple things that do not tempt us to invoke design. Dawkins is quite clear that he wouldn't have had a good answer for the design argument before Darwin, because there is just, I mean, he basically defines biology as the study of things that look designed for a purpose. But, says Dawkins, and as usual with Dawkins, the writing is so clear that it's sort of delightful to read, even when you disagree with him. What he's saying here is, thanks to Darwin, I think biological things are the result of physical processes, and, he says, physics won't tempt us to invoke design in the same way that the hummingbird will. If we look at physics, we'll see simple things, and we won't get that sort of design intuition clicking off in our heads. So, in other words, what Darwin has supposedly done here is he's not really solved the problem of design, he's moved it. Now, this often gets overlooked by people who just sort of say something like, well, you know, the design argument was very interesting and compelling until Darwin solved it. No, even Dawkins can see it's not solved, it's just moved. You should at some point actually go and check whether physics is going to tempt you to invoke design. But Dawkins, not being a physicist, doesn't actually do this. So we have to ask a fundamental question here, right? Are the fundamental physical processes that shaped our universe boring and unexceptional and unremarkable and typical? The sort of things that don't tempt us to invoke design. Now, how are we going to do this? We're just all going to sit around and stare at some equations and see whether we get the same sort of feeling we get from the hummingbird. Well, Dawkins actually has a method. Here's a quote from the same chapter of the same book. It is true, says Dawkins, there are quite a number of ways of making a living. Flying, swimming, swinging through the trees, and so on. But, however many ways there are of being alive, it is certain that there are vastly more ways of being dead, or rather not alive. You may throw cells together at random over and over again for 1 billion years, and not once will you get a conglomeration that flies or swims or burrows or runs or does anything even badly that could remotely be construed as working to keep itself alive. In other words, says Dawkins, you look at the hummingbird and you think there's the appearance of design. He agrees with that. What is it about the hummingbird that specifically produces this intuition in you? Well, he says, here's one way of analyzing it. If you, in a slightly, unfortunate experiment, that's hopefully a thought experiment, if you reduce a hummingbird to its individual cells, and you get all those cells packaged together by IKEA into a hummingbird kit, and you throw those cells together, at no point, even if you do it for 1 billion years, they're almost certainly not going to fly. Right? You won't get, there's lots of ways to throw the cells together that will fly. There's just way more ways of getting it to not fly. As Dawkins says, there's lots of ways of making a living, but way more ways of being dead, or rather not alive. And that's even giving you the advantage of cells. Cells are remarkably complicated. If you took a cell apart into its pieces and threw those together, those wouldn't fly, so to speak, either. They wouldn't replicate, let's say. So there's a method here. Take it apart, throw it back together at random. Now, how do you take a universe apart? Well, we can give that a go. We can ask the question, what happens if you throw a universe together at random? That's what fine-tuning does. It allows us, it's sort of accidental that we sort of stumbled on this method, but fine-tuning allows us to have a controlled experiment here. Well, it's hard to think of throwing all the bits of a universe together at random, especially where in physics here, the laws matter. Well, what if I kept the laws the same? That's a pretty big concession, to be honest. And I threw the constants together at random. Not to say that that's what actually happened in the universe, but just as a way of getting a handle on, is there anything interesting about the way our universe is put together? Or is there something that will tempt us to invoke design? What happens when you throw a universe together at random? Fine-tuning says it doesn't fly. It won't do anything interesting. So there's a rough shape of the fine-tuning argument. We can go into objections. For example, actually, let me do one of them quickly, the most common one, the multiverse. Maybe there's lots of other universes out there, and they really are throwing constants together at random, and so the right set will end up somewhere. Perhaps these constants vary through time and space, effectively creating a vast number of other universes. Here's my response to that. There's a lot of things to say that could be said, but if we're following our method, the question of whether A can explain B isn't enough. Right? Of course, if you put the cells in the right order, the hummingbird will fly. Well, at least we can assume that, for the sake of argument. There's probably no vitalists around. The problem is not whether this can explain it, but whether there's anything remarkable about what needs to be assumed in the explanation. It's whether the explanation, not whether it's true directly, but whether it itself is fine-tuned. So the question was not whether life can be explained by physics, but whether physics itself produces the same sort of intuition for design that life did. Well, if we're thinking about the multiverse, we need to go down another level. We asked what happens if you throw cells together at random and you don't get something that flies. But biology depends on physics in some way. What happens if you throw a universe together at random? Well, it doesn't fly either, using the controlled thought experiment of fine-tuning by changing the constants. So what we would really need to do is not whether the multiverse really exists and can create our universe, but what happens if you throw one together at random? That's the question we would need to ask. The question is not whether the multiverse is true, but whether it erases the sense of design that we have. And the problem is here, we would want to do something similar with the multiverse that we did with physics as we know it, but we do not have a standard model of the multiverse. We don't have anything like a standard model of the multiverse. We have a number of toy models that sort of half proof of concept. Half of those, I'd say most of those can't handle their own infinities. We're just this question. If you're punting to the multiverse, that's an inappropriate sporting analogy for the United Kingdom. If you're just hoping that the multiverse will solve this problem, you really are just in the dark. You've taken the bat and ball and gone home, and you're refusing to play the game. That's what's happened in the multiverse. All right, with that, I'll say thank you very much. Finish on a gratuitous picture of the book again and say thank you very much. Screen. Thank you.
And also, if you do have questions, if Luke can't hear it, do come up to the.
All right.
I think you'll be all right. Just keep it slow.
Okay. Apropos of your final point on the multiverse, I wonder what you would make of the Stoic argument from infinite regression, that basically the fine-tuning argument is an argument from silence with respect to the potential, not of other universes existing now, but our universe collapsing and expanding and collapsing and expanding. And so, of course, the only universe from which we would be able to ask the question, is this fine-tuned, is the one in which we live?
Yeah, so I think my first answer would be similar to that one. I don't think the point I tried to make, if it's successful, it depends on what sort of structure you're trying to give the multiverse. In essence, what I want to know is, I want to do some physics, dagnabbit. Right? It's a lot of fun. I want to know, will any old recurring universe be life permitting, or do you have to do something special? Because here's a test run of this. The Earth, the distance from the Earth to the Sun. So we've known for quite a while that, if it was this percent closer, 5 maybe, to the Sun, then the oceans would boil off. And if it was this much further away from the Sun, everything would freeze over solid. Okay. And then you say, well, that seems like a nice Goldilocks sort of condition for the Earth, the distance from the Earth to the Sun. Is that the sort of thing that we want to hang a design argument on? And someone might say, look, for all we know, so let's go back about 30 years. Before we knew about other planets around other stars, we say, well, for all we know, there's lots of planets out there. And so somewhere out there is going to be one of them is going to be the right distance from its star. And we just happen, and of course, we're going to be on one of the ones that's at the right distance. So that's a kind of multiverse explanation. How did our Earth get to be the right distance from our star, the sun? Answer, because there's lots of planets out there at lots of different distances from lots of different stars, and the right answer will come up somewhere. But that's not enough. What you need, because you can just take it back a level, what does a universe need to do to produce lots of planets? And now you're in the cosmological constant problem. Any old universe won't make planets, won't make lots of planets. Lots of planets, so you get the right one, is itself needs fine-tuning. So until we can get a handle on will a typical universe bounce at all and bounce in the sort of way that will allow galaxies to form at all, we just don't have a handle on this sort of question. And so that's roughly my answer to this multiverse problem. If you're not trying to do physics and you're just doing philosophy, then I think that's a different question entirely. And me wanting a physical, theory might be slightly inappropriate.
Thank you. Hello from a fellow Sydney sider. How are you?
Very good.
I wanted to ask you, because again, I think someone who's an atheist but who's sort of quite interested in science. Am I coming across okay?
Yeah, it's fine.
Yeah. What are the sort of alternate explanations that your colleagues have said, and what was your sort of co-author's response, and what do you consider them to be missing? Yeah. What's the atheist explanation missing?
Yeah, one of the fascinating things about this is it's in one of these. So I collect objections to the fine-tuning argument. So in the book, we started at A, B, C, D. I think we went up to O. And now I'm up to like 31. I'm out past the end of the alphabet of the things that people say. And it's funny how it's changed over the years. There's loads of them. Geraint. So we spend a chapter getting rid of the ones we don't think are any good. That we went up to O with the ones that are no good. The ones we think are interesting and worth thinking about is the multiverse. That's Geraint's preferred option. There's various reasons for that. Maybe there's in deeper physics, we'll finally arrive at a theory in which there won't be any constants, or in which the constants will have to be the way they are and couldn't have been different. Or we do consider the simulation hypothesis, which I consider to be sort of a bit like a multiverse hypothesis. Or it's either roughly a multiverse hypothesis, or it's just God in disguise. Or theism, obviously, in the we discuss in the book. So one of the objections that's come up a lot recently is people saying, why would God need to fine-tune in the first place? Why not? God could just make life in any old universe. And I think the easiest thing to say to that is if as almost all people who end this argument, when we write it down, I've got a paper called A Reasonable Little Question, if you want to see the nitty-gritty philosophical details of this. It's a probabilistic argument, a Bayesian style argument. You can't answer a probabilistic argument using a mere possibility. That's a general principle that needs to be applied much more generally, right? If I say, look, here's some evidence that it's best explained, or it probably points to or raises the probability of theism, a mere possibility, well, God possibly could have done this, right? A mere possibility doesn't help at all. It can't possibly help, right? You've got to argue that my proportioning of my probabilities is wrong, and a possibility is just a single point in that space. You can move a single point around; it just doesn't change anything. So, there's a trillion arguments. I should say a wonderful set of papers by John Hawthorne and Yoav Isaacs called, one of them's called Fine-Tuning, which is very nice, and something like Misapprehension, blah, 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 something else by them. Look at it. Google will find them for you. Does a very good job of dealing with a bunch of standard objections.
Thank you.
Well,
Thanks, Dr. Barnes, for your talk. I was wondering, like, what do you say to someone who is a kind of anti-realist about physics, who said, look, these are interesting theoretical entities that we could move around, remaining mathematically consistent, but maybe I'm convinced by some kind of pessimistic meta-induction, something like that, and I think that's all very interesting, but there's no like touch with reality, and so I don't need an explanation because I don't think that physics is touching reality in the right kind of way.
Yeah, I don't get that one very often. There's a question of do I have to defend some sort of realism in order to make the fine-tuning argument work? I think there's pretty good reasons to be some sort of realist, maybe not a naive realist. The name gives that one away, but some sort of, we're definitely doing something in physics. Along the lines of there's a sort of no miracles argument. If our physical laws don't say something about reality, then it's a miracle that they continue to be predictive. So I'm happy to sort of take that on, but I think actually pulling it back a step, I'm using the laws as we have them, as we see them, which do at least good predictive work for us. The standard model of particle physics, standard model of cosmology. I'm using those to create a sort of a space against which I can compare our universe. So intuitively, we compare the hummingbird, the flying bird we have, to what happens if I pull all of its, unfortunately, all its cells apart and then throw them back together at random. And the answer for most of those cases would be gross, right? Something disgusting, right? The probability of something flying away is very small. So we have an intuition there of what the other possibilities for. Let's throw the bits of throw the cells together at random. How can we do that for universes? We just all sit around and just imagine some universes. Or what I'm doing is I'm using the equations as we have them to sort of create a sort of counterfactual set of other possible universes. So I think, and again, I'm an astronomer, not a philosopher. But I think I don't have to buy a complete, perfect, real connection between one-to-one, at least, or anything like that. Am I loud? Do I need to go back, or what happened? Am I still? Hello?
Just cut out, yeah. Yeah, I think that'll be fine. Can you hear us?
Yes, I can hear you.
Oh.
How much of what I just said did you miss?
The audio output.
I promise I didn't touch anything.
MacBook speaker. Can you hear us?
Yes, I can hear you.
All right.
Sorry.
Well, I suppose this should hopefully be loud enough.
Okay. All right. So I was mid-rant there. Where did I get up to?
got to.
So let me just, I'll start from somewhere, and if I repeat myself, I'm sorry. But roughly, here's the idea. I'm using the equations as we have them to construct a sort of counterfactual set of universes. And I don't think I need much realism at all. I'm just saying if whatever existed was the sort of stuff that would be described by this law to some level of accuracy, if there happened to be anyone in that universe, what else would happen in that universe, right? The sort of law in which the sort of possible universe in which the best law of nature to describe it, had no nuclei or just had free roaming neutrons. I don't have to say what a neutron really is to sort of say, look, nothing interesting is going to happen in that universe. So I would love someone who has a stronger background in philosophy to think through that a bit more. But I don't think I have to defend realism. I just need there to be some sort of connection between the equations and what reality would be like if these numbers had been different.
Hi, thanks. So, the question I have about people who posit multiverses is, I don't know, it just sort of sounds to me quite ad hoc, sort of, I don't know, for want of a better word, kind of desperate to appeal to a multiverse at this stage, given that, I mean, if there is no sort of independent reason to accept a multiverse other than it's sort of getting you out of the argument. Yeah, I'm wondering if you can comment on that. Do you think that this sort of appeal to multiverse is defensible, or is it just a kind of like top attempt to get out of the argument?
I think there's certainly a complement here to the argument that's what you think is needed to refute it or provide an alternative conclusion, and I think that's very interesting. That here is a chain of arguments that seems to go towards a creator. You want to derail that train. What do you have to sort of do? And the answer is, infinite other universes that we can't possibly observe. Well, that's kind of interesting. However, as a physicist, the multiverse might be true. And it seems a fairly natural thing to wonder about on some sort of level, even if you're not thinking about the fine tuning might make it more desperate, as you say, but it's worth considering. So if someone really could come up with a model that is simple, has some sort of universe generator that is simple and produces the universe we see around us in some sort of natural way, and it makes it likely that we would observe this sort of universe, that would be something. I mean, ultimately, the multiverse has a chance to explain something. There is really the values of these constants. If you had some idea about how universes are generated via some mechanism, and at the end of the day, it predicted something like the mass of the electron, not as a single prediction, but as the thing that life would most likely see, or an observer would most likely see, or something like that, that would be interesting. And if we could get lots of those constants and start knocking them off and predicting them, that would be quite interesting. So my main complaint about the multiverse is the thing that it's supposed to be. If it's trying to be science, then do science, dagnabbit. Like, give me a theory, give me something I can do some predictions with and see whether you're right or wrong. But at the moment, they're sort of toy theories that don't, you're not even sure if you're getting the right predictions out of them. We're at that sort of level. Like, they're so sort of ill-formed.
Thank you.
Thank you so much for your talk. I was curious, you mentioned that your co-author is an atheist, but have you had any interactions, whether it's with colleagues or students, where after presenting this information, they've come up to you or said, I'm now seriously considering theism, or my mind has changed because of the presentation of the fine-tuning argument?
I get the occasional email from people. It's more often someone will say, I grew up a theist, and then someone challenged me, where's the evidence? And I realized I didn't have any, so I went looking around and then found the fine-tuning argument. I was like, oh man, that's awesome. It's a bit of a whew. That's more common. I should say, though, there's a group of people I know, I think in Houston, and there's a group of people who ran, it's the Atheist Christian Book Club, where they got together every month, and there was a book that everyone read on sort of atheism, Christianity, and they would discuss it. And it got big enough that they started, they're like, we're big enough. They started inviting like authors. They'd read a book. They read my book at some point, and then had me come and have a chat with them. And literally a couple of months ago, I got an email from, there's two main organizers, a Christian and an atheist. I got an email from the Christian who said, the atheist guy is having a bit of a crisis of non-faith and wants to chat to you a bit more about the fine-tuning argument. And I'm not sure where that's headed, but we just had a, let's Zoom. I'm obviously in Australia. I can't go to Houston, but, and he sort of like it's dawning on him that this is things are starting to make sense for him. So it does hit people. I think it certainly strikes. Well, I once gave a talk to a group called Skeptics in the Pub in New Zealand, where and the interesting thing was not that I changed a bunch of minds, but the room, once I'd presented basically what I presented for you, started arguing with itself. Right, everyone thought, oh, we cannot possibly leave this thing alone. Right, it's I won't be a skeptic if this thing keeps on going. So there must be something wrong here. But the room couldn't decide on what was wrong with the argument. Some people thought the multiverse, and some thought the multiverse was crazy. It had to be this. So it does. I have seen it move people towards theism, at least, but at least does light some fire underneath some people's backsides.
I have another question. I appreciated your response to the kind of realism, anti-realism question. For what it's worth, I'm a Christian too, and I quite like the fine-tuning argument. I'm just wanting to wrestle with some objections that I hadn't seen responded to in the literature. Another objection that comes up is Draper's understated evidence worry, where the general idea is, look, if you take these like large-scale facts about the world, you might think that they point in the direction of theism, but then if you try to precisify the facts under question, you find out that these smaller facts support naturalism or something like that. And I think in this case, he wants to say something like, look, you might have these fundamental constants and quantities pointing towards theism, insofar as they support life. But if you were to look at the universe, you then might expect life to be a lot more abundant. But nonetheless, we seem to be the only universe with life on it, at least if you accept Fermi paradox results and that kind of thing. Then this might seem to support naturalism. Do you have any thoughts on that response?
So I think here it's a battle of the expectations. And it's a battle. This is why putting it in Bayesian terms is quite useful. It's would you expect this sort of universe on theism versus would you expect it on naturalism? And there's various things you can raise about the universe which you might not have expected on theism. And I think the problem of evil it could be fleshed out in those sorts of terms. Would we expect life to be more abundant? Yeah, maybe. The thing is, I find that, even the problem of evil, that it's sort of small change relative to the magnitude of the problem that naturalism faces. If you think that this whole, let's just vary the constants, get a range of things, just see what's going on. The sort of numbers you get out of that, for the cosmological constant, for the masses of the particles, the cases I've shown you, you get up with probabilities. So I fleshed this out in a reasonable little question. 10 to the 130, one chance in a number with 130 digits in it, or 136 or something, whatever. Like just absurdly small numbers come out of the would I expect this universe on naturalism, and it just makes all these other worries into some very, very small pocket change relative to that. In other words, I can make a lot more sense out of this universe if it's made by a creator, but I don't know everything about why it's this way, rather than assuming that it's just a naturalistic universe in which the fact that there's atoms at all now becomes an astounding and quantifiable mystery. With the abundance thing, I actually think there's would we expect more life out there? First of all, if theism expects there to be more life, it surely counts against it that naturalism expects there to be absolutely none, right? You've just got to weigh these things up. But there are reasons why the universe has the empty spaces that it has within the system as it is. You might not expect it a priori, but we understand. If the solar system were filled with air, the Earth would spiral into the sun within a couple of months, thanks to air pressure, air friction, whatever the word I'm thinking of, air resistance. Thank goodness. I'm a physicist after all, right? So It's not that, I mean, God, yes, God could perform a perpetual miracle to have a solar system full of air and have us keep going around and everything be fine. But look, there's just a way, the way things are set up has a logic to it, and that involves the empty spaces. The empty spaces are part of the way our universe is put up. We need those for life, at least in this way. So that's not that I think that, you know, I've got an argument to prove that if God existed, then, you know, it's 90% sure that this is the way the universe would be, or anything like that. It's just these worries don't get us anywhere near the improbabilities that naturalism really has to try and face up to.
Is there one more question? If not, then yeah.
Yeah, I had a question about the number, the 10 to the negative 136 that comes up in your paper. If I'm reading you correct, that's something like a kind of most charitable possible kind of number. Is that right? That's sort of like the actual number could be much smaller if we studied more constants and studied more variation and so on.
Yeah.
I'm wondering, maybe this is an unanswerable question, but do you have a hunch as to what like the sort of actual number might look like?
Oh, yeah, very hard to know. The ways I'm being charitable are, there's a couple of cases where we're not, you know, you've actually, with this sort of, you do have to do some physics, right? You have to do the calculation to work out what would happen. For some of them, there are just enough uncertainties that I can just shelve a couple of cases and still get a really small number. The other thing is, we're only, as I said, these are very basic arguments about whether something is stable or not. If I had like a fully finished, if I could get particle physics to go all the way from here's the fundamental law of particle physics of, you know, quarks and electrons, all the way up to, and here's how out of that you build a cell, right, all the way up, but all those calculations, I could do all of those. Man, you could have a lot of fun really nailing down, fun for me, what electron mass you need to get cells right or to get this right. Like, and it'd be a much more complicated case, but I suspect there's all sorts of interesting ways in which the constants are fine-tuned, not just so one thing sticks to another, but so that, say, the origin of life could happen, or DNA could do the right thing, or I suspect all of those. I can't prove it at the moment. This would be some sort of super fine-tuning argument, but I certainly suspect more cases. But, you know, 10 to the 136 seemed like a pretty impressive number as it is.
A final round of applause for Scott's.
Thank you.